Guy ILS Montessori and School. Grade 9, Physics. Federal Board Islamabad, 2025 onwards syllabus. Summary of Chapter 5. Dynamics 2, from Cantab Publisher Book, Federal Board Islamabad. Chapter 4, Dynamics 2 from NBF Book, Federal Board Islamabad. Introduction. Forces play a crucial role in shaping the motion and behavior of objects. Some forces require direct contact, while others act over a distance. Based on this distinction, forces are categorized into contact forces and non-contact forces. Understanding these forces helps us explain everyday interactions, from pushing a door to the Earth's gravitational pull on objects. Contact forces. Contact forces occur when two objects physically interact. These include friction, tension, normal force, and air resistance. Their effects depend on factors such as the roughness of surfaces and the properties of materials. Once the contact is broken, these forces no longer act. Effects of contact forces. Contact forces can change an object's direction, speed, or shape. Changing direction. When a ball is bounced against a wall, the wall exerts a force that alters its direction. Changing speed. A soccer ball's speed changes when a player kicks, volleys, or backheels it. Changing shape. Kicking or stepping on a soccer ball temporarily deforms it, demonstrating how forces can alter an object's shape. Non-contact forces. Non-contact forces act without physical contact. These include gravitational, electrostatic, magnetic, and nuclear forces. Their strength varies based on distance and the inherent properties of objects involved. Let's explore some examples. Gravity, the force of attraction between objects with mass. It keeps planets in orbit and determines our weight on Earth. Magnetism, a magnet creates a field that exerts force on magnetic materials within its range. Static electricity, a charged object generates an electric field, which influences other charged objects nearby. Different types of contact and non-contact forces. 1. Gravitational force. Gravity is one of the most fundamental forces in the universe. According to Newton's law of universal gravitation, the force of attraction between two objects is directly proportional to their masses and inversely proportional to the square of the distance between them. Equal and opposite, the gravitational force between two objects acts equally on both, but in opposite directions. Effect of mass, doubling the mass of one object doubles the gravitational force. If both masses are doubled, the force increases 4 times. Effect of distance, if the distance between two objects is doubled, the gravitational force reduces to 1/4 of its original value. Gravity governs the motion of celestial bodies, keeps the moon in orbit around Earth, and determines an object's weight. Instruments like a spring balance measure gravitational force, allowing us to quantify weight. 2. Friction. When two objects come into contact, they resist sliding or moving against each other due to a force called friction. This force counteracts any effort to make the objects slide past one another. The amount of friction depends on the texture of the surfaces. Smooth surfaces have lower friction, while rough surfaces exhibit higher friction. 3. Drag force. Fluids, such as air and water, create resistance when objects move through them. This resistance is called drag force or fluid friction. It occurs due to the interaction between the object's surface and the fluid. Streamlined shapes help reduce drag, as seen in the design of objects like javelins, which cut through the air efficiently. In contrast, bulky objects like a cardboard box experience more air resistance and slow down faster. 4. Air resistance. Air resistance, also called aerodynamic drag, opposes the movement of objects through the air. It plays a crucial role in aviation and automotive design. The amount of air resistance depends on the object's speed and surface area. It arises from friction between air molecules and the object's surface, as well as turbulence that creates pressure differences. These factors hinder smooth motion and require more energy for movement. 5. Tension. Tension is a pulling force that occurs along a string, rope, or cable when it resists being pulled apart. Rock climbing ropes are designed to stretch slightly, creating tension that prevents injury during falls. Whether the material is elastic or inelastic, tension ensures stability and support. 6. Elastic force. When a material like a rubber band or a spring is stretched or compressed, it experiences a force that tries to return it to its original shape. This restoring force is called elastic force. Hooke's law states that the force is directly proportional to the deformation, up to the elastic limit. Beyond this limit, permanent deformation occurs, and excessive force may cause breakage. 7. Electric force. Electric force results from the interaction between charged particles in atoms. Protons are positively charged, electrons are negatively charged, and neutrons are neutral. Normally, objects are neutral, but if they gain or lose electrons, they become charged. Opposite charges attract, while like charges repel. The strength of the electric force depends on the magnitude of the charges and their distance from each other. 8. Magnetic force. Magnetic force is a non-contact force that occurs between magnets. A naturally occurring magnetic rock, lodestone, was discovered by the ancient Greeks. Magnets have a north pole and a south pole. Like poles repel, while opposite poles attract. Current-carrying conductors produce a magnetic field, making them electromagnets. Magnetic force is also the principle behind magnetic levitation trains. 9. Thrust, driving force. Thrust is the force that moves objects forward. It is essential for vehicles like rockets, airplanes, and boats. Jet engines in airplanes mix air and fuel to create a powerful forward push. Rockets use rapidly escaping gases to lift off. Boats use propellers to push water backward, creating a reaction force that moves them forward. Thrust helps these vehicles overcome resistance and move efficiently. 9. Normal force. When two objects touch, they exert force on each other perpendicular to their surfaces. For example, when holding a box, your hand pushes it up while the box pushes down due to its weight. This opposing force between surfaces in contact is called the normal force. It acts perpendicular to the contact surface and helps balance objects in stable positions. Fundamental forces in nature. Introduction. Before diving into the complexities of fundamental forces, it is important to understand that these forces govern every interaction in the universe. They shape the very fabric of reality, influencing everything from the movement of celestial bodies to the smallest atomic interactions. By studying these forces, we gain deeper insights into physical interactions and the remarkable contributions of scientists, including those from Pakistan, to our understanding of the universe. Fundamental forces of nature. Humans have always sought to understand the universe in a simple yet meaningful way. Just as physicist Richard Feynman imagined smaller wheels inside larger ones, scientists have tried to uncover the fundamental rules governing nature. Initially, they identified 5 main forces: gravitational force, electric force, magnetic force, strong nuclear force, and weak nuclear force. However, the work of Faraday and Maxwell led to the unification of electric and magnetic forces into what is now known as the electromagnetic force. Today, modern physics recognizes 4 fundamental forces. 1. Gravitational force. This is a long-range force responsible for various phenomena such as tides, the motion of planets, and the large-scale structure of the universe. It is the force that keeps celestial bodies in their orbits and governs the attraction between masses. 2. Electromagnetic force. This force is also long-range and plays a crucial role in chemical reactions, the binding of atoms and molecules, and the formation of structures like crystals and buildings. On a microscopic level, it explains forces such as friction and adhesion that affect everyday life. 3. Strong nuclear force. This is the most powerful of all fundamental forces, responsible for holding protons and neutrons together in the nucleus of an atom. It overcomes the natural repulsion between positively charged protons by acting through particles called gluons. These gluons work like glue, binding quarks together to form protons and neutrons. 4. Weak nuclear force. This short-range force is responsible for radioactive decay and certain nuclear processes. It plays a significant role in energy production in stars and other nuclear reactions. A major breakthrough occurred in 1979 when Sheldon Glashow, Steven Weinberg, and Dr. Abdus Salam were awarded the Nobel Prize for their work in unifying the electromagnetic force and weak nuclear force into a single concept known as the electroweak force. Representing forces. Understanding forces requires not only theoretical knowledge but also visual representation. Free body diagrams are a crucial tool for analyzing forces acting on an object. These diagrams help in isolating and examining forces in a clear and simplified manner, making it easier to understand their effects. Understanding free body diagram. External forces acting on an object may include friction, gravity, normal force, drag, tension in a string, or a human force due to pushing or pulling. Suppose a book is pushed over the surface of a tabletop as shown in figure. Then how can we represent the forces acting on the body using a free body diagram? Free body diagrams are used to show the relative magnitudes and directions of all the forces acting on an object in a given situation. In other words, a free body diagram is a special example of the vector diagrams. Usually, the object is represented by a box and the force arrows are drawn outward from the center of the box in the directions of forces as shown in figure. The length of a force arrow line reflects the magnitude of the force and the arrowhead indicates the direction in which the force acts. Each force is labeled to indicate the exact type of force. This is a free body diagram showing the forces acting on a 10 kg object. Force normal, green, upward, the normal force exerted by the surface. Force gravity, black, downward, the gravitational force, weight. Force applied, blue, rightward, the applied force pulling the object. Force of friction, red, leftward. The friction force opposing motion. It visually represents the magnitude and direction of forces acting on the object.
Balanced forces. When forces are balanced, meaning they are equal in size but opposite in direction, they cancel each other out, resulting in no change in the state of the object. This leads to two outcomes. An object at rest will not start moving. An object in motion will continue moving at a steady speed and in the same direction. Examples. These tug-of-war teams are pulling with the same amount of force in opposite directions. The forces are balanced, so nobody moves. When you place a book on a table, the force of gravity still acts on the object but the object doesn't fall. That is because its weight is balanced by an upward force from the table. Balanced forces can also act on a moving object. When a skydiver reaches maximum velocity, the forces of air resistance and gravity that act on the skydiver are balanced. Unbalanced forces. Unbalanced forces are those that do not cancel each other out when acting on an object. The net force acting on the object is not zero. Unbalanced forces lead to a change in the object's state of rest or motion. This change can be in terms of speed, direction, or both. Due to these changes, acceleration will be produced in the object. Examples: if you apply a strong enough force on a stationary sled as shown in figure to overcome the friction between the sled and the ground, the sled will start moving, showing the effect of the unbalanced force. The engine provides a force that propels the car forward. If this force is greater than the resistive forces, like friction and air resistance, the car will accelerate. This is illustrated in figure 5.22. Resultant force. When forces act on an object along the same straight line, their resultant, or net force, can be determined by simple arithmetic. The principle is straightforward. Forces acting in the same direction are added together. Forces acting in opposite directions are subtracted from one another. If two or more forces act in the same direction, their magnitudes, sizes, are simply added together to determine the resultant force shown in figure. If two forces act in opposite directions along the same line, you subtract the smaller force from the larger force to determine the resultant force as shown in figure. The direction of the resultant force will be in the direction of the larger force. When dealing with more than two forces, simply follow the same process. Sum up forces in the same direction and subtract those in the opposite direction. This is shown in figure. This picture shows a person riding a bicycle, and it helps explain the different forces that act on the bicycle when the person is moving. Here's a simple explanation of the forces for students. Applied force, purple arrow. This is the force that the cyclist creates by pushing the pedals. It helps the bike move forward. Friction. This is the force that tries to slow down the bike. It comes from the contact between the wheels and the ground. It works in the opposite direction to the way the bike is moving. Air resistance, blue arrow. This is the force that pushes against the cyclist as they move forward. It makes it a little harder to go fast, just like when the wind blows in your face. Normal force, upward blue arrow. This is the force from the ground that pushes up on the bike. It helps keep the cyclist and the bike from falling through the ground. Gravity, red arrow. This is the force that pulls everything toward the earth. It pulls the cyclist and the bike down toward the ground. When the cyclist pedals, the applied force is greater than the forces trying to slow down the bike, like friction and air resistance, so the bike moves forward. In equation, the overall force, called the resultant force, is calculated by subtracting the forces that resist motion, friction and air resistance, from the applied force. This is why the bike can move forward. In simple terms, when you ride a bike, you use your legs to push the bike forward, and things like the ground and air try to slow you down. The stronger you pedal, the faster you'll go. Newton's laws of motion. In the world of science, the laws of motion formulated by Isaac Newton in 1687 provide a fundamental understanding of how objects remain stationary, move, or alter their direction, as well as how interacting entities exert forces on each other. When we want to change the speed or direction of motion of an object, a force must be applied. This concept is a cornerstone of classical mechanics, which explains the relationship between motion and force. Let's learn definition of first law. The first of these laws, known as the law of inertia, directly illustrates this concept by stating that a body remains in its state of rest or uniform linear motion unless compelled to change that state by an external unbalanced force. Applying Newton's first law. In the vacuum of outer space, devoid of air resistance, a thrown ball would persist in its trajectory at a constant velocity indefinitely, only altering its path or speed upon encountering an external force, such as a planet's gravitational influence or an impact with another entity. Similarly, a book resting on a table remains stationary, as the force of gravity acting on it is precisely counteracted by the table's upward normal force, resulting in a net force of zero. When we think about a moving object, the real question is not about what makes it keep moving, but what can change or halt its state of rest or motion? This law tells us that the state of an object can change only when it experiences some resultant, net, force. Inertia. What is inertial? Let's learn the concept. Newton's first law predicts the phenomenon of inertia, which is the natural tendency of an object to resist changes in its state of rest or motion. Inertia is a property inherent to all objects, influencing how they respond to forces. For example, when you are riding in a car and it suddenly stops, you might lurch forward, as shown in figure. This happens because your body, due to inertia, wants to keep moving forward even though the car has stopped. Another example involves placing a large coin on a card that rests on your finger as shown in figure. If you flick the card away quickly, the card moves, but the coin drops straight down onto your finger. This happens because the coin, due to its inertia, resists the sudden change in motion. The coin wants to stay in its current state, at rest, until a significant force compels it to do otherwise. Mass is a measure of inertia. Let's learn this concept. It is more difficult to move a stationary truck than that of a stationary car. So, we can say that the larger the mass of an object, the greater its inertia. Because of this, we can consider mass to be the quantitative measure of inertia. Newton's second law of motion. Often, an object is subject to multiple forces beyond the applied force, such as friction or air resistance. In this context, the term force refers to the unbalanced force, which is also called net force, resultant force. Newton's second law of motion articulates this relationship, stating 1. More force results in more acceleration. 2. Acceleration decreases with an increase in mass. Net force acting on an object produces acceleration in its direction, which is directly proportional to the net force and inversely proportional to the object's mass. Mathematically, AF, and is read as acceleration is directly proportional to the force. This means that as the force applied to an object increases, its acceleration increases proportionally. The second equation, a 1/m, is read as acceleration is inversely proportional to the mass. This means that as the mass of an object increases, its acceleration decreases. On combining the above expressions, F equals ma and this formula, F equals ma, is read as follows. F stands for force, m stands for mass. A stands for acceleration. It is Newton's second law of motion and can be stated as, the force acting on an object is equal to the mass of the object multiplied by its acceleration. This means that the amount of force needed to accelerate an object depends on both the object's mass and the desired acceleration. Unit of force. Unit of force is a Newton, which is the force needed to accelerate a 1 kilogram object by 1 meter/s squared, read as 1 meter per second squared.
Newton's third law of motion. After understanding the determination of force and its effects, we now explore the behavior of objects when they interact. Real-life scenarios shed light on this phenomenon. For example, when you walk, there is a secret teamwork between your feet and the ground. Your feet push on the ground, and at the same time, the ground pushes right back on your feet. Think about a car driving. Its tires press down on the road, but the road is not silent. It pushes right back on the tires. They are working together, at the same moment, like partners in a driving process. Action, tire pushes on road, reaction, road pushes on tire. In the above examples, forces are in the form of pairs. We call them action and reaction. Newton described all such phenomena by stating a law called Newton's third law of motion. This law states that action and reaction are equal but opposite. Action: rocket pushes on gas. Reaction: gas pushes on rocket. Action: man pulls on spring. Reaction: spring pulls on man. Action: earth pulls on ball. Reaction: ball pulls on earth. Push of table on book. Push of book on table. Action: earth pulls on ball. Reaction: ball pulls on earth. Action and reaction: the boat moves backward when you step forward. Now let's try to understand the concept that forces exist in pairs. Let us understand the effects of action and reaction on objects. When one object exerts a force on another object, according to Newton's third law of motion, the second object exerts a force of equal magnitude but in the opposite direction on the first object. These forces act on different objects, not on the same one, which is a key point for grasping how interactions happen in the physical world. Let us link this concept with an everyday example. Imagine two ice skaters standing still on an ice rink as shown in figure. If one skater, object A, pushes the other skater, object B, away, both skaters will move in opposite directions. This movement occurs because object A exerts a force on object B, and in response, object B exerts an equal and opposite force on object A. This scenario perfectly illustrates Newton's third law in action, indicating that forces always exist in pairs. A exerts a force on B, accelerating it. Therefore, the effect of the force of A on B is not cancelled by the effect of the force of B on A. This time, both A and C exert forces on B. They can cancel each, B, other. If they do, B does not accelerate. Do action and reaction cancel each other's effects? Now, let us examine a more complex situation of an orange and an apple linked together, as shown in figure. They exert forces upon each other, but no other forces act upon them from outside their system, so they form an isolated system. The forces they apply to each other during their interaction are internal forces. Despite these forces being equal in strength and opposite in direction, they do not cancel out the effects they have on each individual fruit. This might seem strange at first, but it is because these forces are acting on separate objects. The orange can affect the apple, and the apple can affect the orange, causing each to change speed or direction. However, if we look at the system of the orange and apple together, these internal forces are in balance, and as a result, there is no net acceleration for the system as a whole. Action and reaction forces are of same type. An important aspect of Newton's third law is that it makes no distinction between which force is the action and which is the reaction. Both forces occur simultaneously, have the same strength but in opposite directions, and are of the same type, e.g., both are pushes, pulls, or gravitational forces. This symmetry highlights the law's universal applicability, whether we are looking at objects on Earth or astronomical bodies in space. Here are some illustrations. Pushing a box. If you push a box forward, your force on the box is a pushing force. The box pushes back on you with an equal force. Thus, both the action and reaction are of the same nature. They are both pushing forces. Gravitational attraction. The Earth pulls an apple downwards due to gravitational force, as shown in figure. The apple pulls the Earth upwards with an equal gravitational force. Even though we don't notice the Earth moving because of its huge mass, the forces are still equal. Both are gravitational forces.
Grade 9 Physics. Chapter 5 Dynamics. Limitations of Newton's laws. As we go deeper into the realm of motion, It is essential to acknowledge the inherent limitations of Newton's laws. While these laws offer a robust framework for understanding motion in everyday scenarios, they provide approximations rather than exact descriptions. Let us discuss it. Effects of high speed. Newton's laws provide an excellent framework for understanding the motion of objects at everyday speeds. However, as velocities approach the speed of light, reality diverges from these classical predictions. Time dilation and mass increase are among the peculiar phenomena that occur, which Newton's laws cannot account for. This is the realm of Einstein's theory of relativity, which introduces concepts such as the interchangeability of mass and energy, encapsulated in the famous equation E=mc². At such high speeds, as objects gain energy, their mass equivalently increases, demanding ever greater forces to achieve further acceleration. These relativistic effects, distinct from the Newtonian experience, demonstrate the need for Einstein's adjustments to our understanding of physics at near light speeds. Quantum effects, very small things. There is another limitation of Newton's laws. This is about really tiny things, like atoms and subatomic particles, like electrons. In the world of these tiny particles, things do not act like they do in our normal world. For instance, a particle can be in two places at once or behave like a wave instead of a solid object. This sounds really strange, right? Newton's laws cannot explain these bizarre behaviors. So, scientists use quantum mechanics, a different set of rules, to understand how these tiny particles act. Quantum mechanics shows us a whole new world of possibilities that are very different from our everyday experiences. In reality, all laws of physics are approximations. Newton's laws are a very good approximation for conditions where velocities are much smaller than the velocity of light. At near light speed, Einstein's relativistic mechanics are more effective and explain all the relativistic effects. Equilibrium. In general, equilibrium refers to a state of balance. In physics, equilibrium refers to the condition where there is no net external force acting upon an object or system. This does not mean there is no force acting, but rather the vector sum of these forces is zero, leading to no change in the state of the system. So, a body in equilibrium is either in a state of rest or in a state of uniform motion, uniform velocity. There are two main conditions of equilibrium. Translational equilibrium. If the body is at rest or moving with uniform velocity, then the net external force acting on it will be zero. Under this condition, the body is said to be in translational equilibrium. A book at rest on a table exemplifies translational equilibrium, where the downward gravitational force, its weight, is precisely counterbalanced by the upward normal force exerted by the table. Similarly, a raindrop descending at a constant velocity achieves translational equilibrium through the equilibrium of gravitational pull and air resistance. Here, the drag force exactly offsets gravity, rendering the net force null. Rotational equilibrium. If an object is in uniform rotational motion, or at rest under the action of forces tending to rotate it about a fixed line, then the rotational effects of forces acting on the object cancel each other out. Under this condition, the body is said to be in rotational equilibrium. When a fan spins at a consistent speed, it exemplifies rotational equilibrium, as it maintains uniform rotational motion without speeding up or slowing down. Similarly, Consider a seesaw balanced horizontally with two children of identical weight seated at equal distances from the pivot. In this scenario, one child's weight attempts to rotate the seesaw in one direction, while the other child's weight exerts an equal force in the opposite direction. This balance of forces allows the seesaw to remain level, demonstrating rotational equilibrium by the equal and opposing forces that prevent any change in the seesaw's motion. One. Static equilibrium. If an object under the action of forces remains at rest, then it is said to be in static equilibrium. The net force on the object must be zero. The rotation effects of forces acting on the object must also be zero. Dynamic equilibrium. If the object remains in uniform motion under the action of forces, then it is said to be in dynamic equilibrium. When an object is at rest, i.e., in static equilibrium, then it may be in a stable, unstable, or neutral state. Primarily, static equilibrium is classified into three types depending on the state of the object. Stable equilibrium. An object is said to be in stable equilibrium if, when displaced slightly from its equilibrium position, it returns to its initial position. The object will resist any displacement away from this equilibrium. Imagine a bowl with a ball sitting at its bottom. If you slightly push the ball, it will roll a bit and then come back to its original position at the center of the bowl. Unstable equilibrium. On the other hand, an object is in unstable equilibrium if, when slightly displaced, it moves further away from its original position. Place a ball carefully at the very top of an inverted curved dish. 1. In this position, any slight disturbance will cause the ball to roll off the dish. The ball has no inclination to return to its original position at the top. Instead, it continues to move away, indicating unstable equilibrium. Neutral equilibrium. A system is in neutral equilibrium if, when displaced slightly, it remains in its new position without returning to its original position or moving further away. An example of neutral equilibrium is observed when a sphere is nudged on a flat surface. It moves to a new position without exhibiting any tendency to return to its original position or to move further away as shown in figure.
Friction. Friction, denoted by F, is the resistance to relative motion that occurs when two materials come into contact, whether they are solids, liquids, or gases. Since friction is a force, it is a vector quantity and is measured in newtons, N. It always acts in the direction opposite to motion. For example, when a block is pushed to the right, friction acts to the left. Similarly, when an object falls through the air, friction, air resistance, acts upward. Microscopic description of friction. No surface is perfectly smooth. Even highly polished surfaces appear rough when examined under a microscope. Due to this roughness, the interlocking of surfaces creates friction. Sliding friction occurs when two objects move against each other, such as the friction between brake pads and bicycle rims that slows down wheels. Rim brakes work using this principle, where pulling the brake lever moves pads against the wheel rim, causing it to stop. Advantages and disadvantages of friction. Friction is useful in daily life. It helps us walk, allows vehicles to move by creating grip between tires and the road, and holds screws and nails in place. However, it also has disadvantages. It slows down moving objects, generates heat in machinery, wastes energy, and causes wear and tear of mechanical parts. Methods of reducing friction. Unwanted friction can be reduced using different methods. Polishing surfaces makes them smoother and decreases friction. Using ball bearings changes sliding friction into rolling friction, reducing resistance. Applying lubricants like oil or grease between machine parts minimizes friction, preventing excessive wear and energy loss. Let's discuss methods of reducing friction. 1. Rolling friction. When a spherical ball, ring, or cylinder rolls, it experiences rolling friction, which is much smaller than static or sliding friction. This is why wheels make transportation easier. Rolling friction allows heavy objects like deep freezers with wheels to be moved effortlessly. 2. Fluid friction. Liquids and gases, known as fluids, exert force on objects moving through them. When an object moves through a fluid, it experiences a retarding force known as drag. This force slows the object down as the fluid pushes back with equal force, as explained by Newton's third law. Fluid friction affects vehicles, airplanes, and swimmers moving through water or air. Centripetal force. Centripetal force is the force that keeps an object moving in a circular path. It acts toward the center of the circle and is responsible for changing the direction of the object's velocity, keeping it in motion along the curved path. Formula of centripetal force is as in the figure. The mathematical expression for centripetal force is, where Fc equals centripetal force, m equals mass of the object, v equals velocity of the object, r equals radius of the circular path. Example of centripetal force. Motion of planets around the Sun. The gravitational force acts as the centripetal force, keeping planets in orbit around the Sun. Car taking a turn. When a car takes a turn on a circular road, friction between the tires and the road provides the necessary centripetal force to keep the car on the curved path. Swinging a stone with a string. If you swing a stone tied to a string in a circular motion, the tension in the string acts as the centripetal force, pulling the stone towards the center.